Hello, everybody, and welcome to Neuroscience for Numpties. I'm your host, Joe, and I hope you're all having a wonderful day. In the previous episode, I covered, for the first time, a brainwave-based lie detection article, one of the first brainwave-based lie detection articles in existence. And today, I wanted to back up and cover the actual signal from the brain that was being measured in that article. And I also want to talk a little bit about the recording equipment that is used to obtain that brain signal, and talk about kind of what are some of the challenges with that brain signal, and also hopefully explain to you guys the basics about how the brain actually produces electricity, which is kind of an interesting concept. I don't want to get too far down into the weeds about all of that, but I'm hoping by the end of this episode you guys will have a basic introduction to some of those concepts, and that will really help moving forward in the rest of the season as we talk about other brainwave-based lie detection articles. So let us jump right into it. I'm going to share my screen. Here we go. Okay. And so this is the article that I covered in the previous episode, The Truth Will Out, and this is by Larry Farwell and Manny Donchin. They're two big names in the field. And this was published in 1991, so that gives you kind of an idea of how early some of this technology was in existence. And truth be told, this is not actually the very first article. Sorry, I'm going to actually move my video over here so I can be looking at the camera a bit better. Okay, so I wanted to note that there actually was another paper that came out around the same time, and this was actually going to be my topic for this episode, and I decided I was going to put this on hold because it was more important to me that you guys had a better understanding of this brain signal and actually how we get signals from the brain in general. So I figured that was maybe a better place to start off with. And truth be told as well, that this article is actually a little bit more complex than the previous article. This article is fairly simple, it's pretty intuitive, and the terminology that we use, or that they used in this article, is the same type of terminology that we use today in 2020. So that makes this article kind of a little bit easier to digest compared to this article. By the way, this article is by a Dr. J. Peter Rosenfeld. Dr. Rosenfeld is the foremost expert in brainwave-based lie detection today. And I actually have the privilege of working in Dr. Rosenfeld's lab. So that is how I know all of this stuff, in case anyone was wondering. Now, to my knowledge, this is actually the first publication on brainwave-based lie detection, and this was written by Dr. Rosenfeld in 1986. It was published in 1987, and he was probably working on it for a year prior to when they submitted it for publication, which was in 1986. So I thought some of you might be interested to know that brainwave-based lie detection has essentially been around since the mid-1980s. And that's incredible. And actually, that is one of the reasons why Neuroscience for Numpties exists in the first place. Is, we've had this technology, brainwave-based lie detection technology, since the 80s. And yet here we are in 2020, and nobody knows about this technology. So that is really the main goal of Neuroscience for Numpties, is to talk about really cool, exciting technology like this, and to introduce it to you guys. I still can't believe how this was more than 30 years ago that we've been able to do this, and yet nobody knows about it. And so it just kind of goes to show you how large of a gap there is between what scientists understand and what the general public understands. So that's why I think it's so important to be doing this. And that's also why I'm starting with relatively old literature, right? I know I said that I wanted to talk about the bleeding edge of neuroscience, but the thing is that there's so much cool technology that nobody really knows about that was invented 30 plus years ago. So anyway, enough about that. Let us get into the topic of the video today. Oh yeah, I wanted to address an issue that I've been talking about, brainwave-based lie detection as lie detection, and so this is something I wanted to address in this video. I can't really call myself a scientist who studies in this field if I keep calling it lie detection, because it's not really lie detection. It's some of the early articles started off by questioning this new protocol as a brainwave-based lie detector. But the reality is that the signal that we measure in the brain doesn't actually measure lies. You can think of, in the literature, they call it the Pinocchio effect. Scientists have been looking for the Pinocchio effect. And if you're familiar with Pinocchio, every time he lied, his nose would grow. So what scientists have been doing for the last 30 years is hoping to find, basically the Pinocchio center of the brain. They're looking for that structure in the brain that lights up every time that you lie. Unfortunately, scientists have not been able to really find that. So, however, I should say, the P300, which is the brain signal that we talked about on the previous episode, it actually does provide really accurate discrimination between guilty people, criminals, and innocent people. However, it doesn't index lies. The P300 is not measuring lies in the brain. It's not that sought after Pinocchio that all the scientists have been looking for. So they thought it appropriate to change the name. Well, if we're not really measuring lies, then what are we measuring? And in terms of P300, it's more that you're looking at knowledge recognition of the crime-relevant probe item. The probe is the terminology I introduced in the previous episode. The probe is like the murder weapon. If you were a murderer, the crime-relevant item would be the murder weapon that you used, and then you have the irrelevant items that were not crime-relevant. Those could be like other weapons that weren't used in the crime. And so the guilty murderer would be expected to recognize the murder weapon, but not the other weapons that that weren't used in the crime. And then innocent people wouldn't recognize any of those items. So in that case, they said, well, this is really a test of knowledge, and that's going to reveal if you were guilty or not. So they called it the guilty knowledge test. But because scientists are kind of a pain in the butt, they decided that that name wasn't good enough, because, well, knowledge can't really be guilty. It's the people that are guilty, not the knowledge. So then they changed it again to the concealed information test, because what are you testing for? You're testing for hidden or concealed information. And the acronym for that is the CIT. So in 2020, we don't call it brainwave-based lie detection. We call it brainwave-based concealed information detection. So I just wanted to clarify that because I couldn't call myself a serious scientist in the field, and I keep using the incorrect terminology. Okay, so this concealed information test, the brainwave-based concealed information test, uses a particular type of equipment, and so I thought I might introduce that equipment to you guys in this episode. It's called an electroencephalograph. That's what we use. It's a fancy word. The acronym is EEG. I was actually going to look that up for you guys here. There's a bunch of different terms. The electroencephalogram is actually the output that you get from the graph. These are the recordings, as it say. It's the test or record, which I'll show you what that looks like a little bit later. The electroencephalograph is the actual machine that you're using, and I'm going to show you that right now. And then the electroencephalography is the actual measurement of electrical activity. So now that that's all clear as mud, let me show you what the device actually looks like. So we're starting with the electrodes here. Now, what is an electrode? So let me zoom in on that. That might be a little bit too far. But anyway, here we go. Okay. So essentially what you have is you have some metal here encased in plastic, a plastic coating. The metal is something that's like a conductive alloy. So this is typically zinc or copper, gold, silver chloride, these types of conductive metals that can pick up on electrical signals very well. And they're going to pick up on the electrical activity in your brain, and they're going to communicate that through a wire into something called an amplifier. You're picking up on signals that are very, very small. So the amplifier is going to do exactly what the name suggests and amplify the signal from your brain. So it makes it a little bit easier to see it. And then that signal is then fed, the amplified signal is fed into a computer. Now, you also have a hole here, you might notice. So here's the plastic, here's the metal, and then there's a hole. And this is the top angle here. So when you look, you can see the hole. And what you do is you put a syringe in that hole, and you use the syringe to administer some goop. It's kind of it's a conductive paste. It's a gel. And what the gel is doing here, pretend that this is the surface of your scalp. And here's the electrode. What you do is you would insert the syringe here and administer the gel. And what the gel would do is soak in through your hair into the surface of the scalp. And it would also cover the metal part here. So then the electrical activity in your brain, which actually makes it to the surface of the scalp, would then travel through the goop and through your hair and to the metal, and then, is transported through the wire. So that's why you put the electrodes on the head, so you can pick up on that activity. That gives you the gist of how that works. Now, after you record the electricity on the surface of the scalp, and you send that to the amplifier, which is then sent to the computer, you get something that looks like this. You get lots of squiggly lines. I'm showing you the output from basically one electrode. You get a lot of squiggly lines, and what you're seeing here is changes in voltage over time. And actually, remember that I said that the electricity, that signal that you're picking up on, is actually really, really small. So we're measuring this in microvolts, which is, I think, 1,000th of a volt. And so what we're doing is, I don't know if I pointed this out to you, but in one of the articles here, there's something called an ERP. That's an event-related potential, and I talked about that in the previous episode. The event-related part of that, first of all, the potential is the signal. That's the brain signal that you're measuring, the electricity from the brain. The event-related part is that you're looking at an image, and then your brain is reacting to that image. So what I have here, this is something called a probe, which is like the murder weapon. This is an item that is crime relevant. So that's why I say it's the murder weapon. And then we're looking at how your brain responds. How does your brain react after it sees that item? And then we can compare that response to how your brain reacts to an irrelevant item that wasn't involved in the crime. And you'll notice here's our little segment that's what we're analyzing here. So then you might move that over here and analyze this segment. And let's say that I presented to you the murder weapon like 30 different times, and then we can average this segment 30 times, so we get a nice stable average. And then we can do the same thing with an irrelevant weapon that wasn't crime related. And I present that picture to you 30 times, and we see how your brain reacts to that picture. And then I've plotted them, the average of those 30 pictures. I've plotted that in a black line here, and I've plotted the irrelevant item as a red line. And you can see that your brain would have little to no response to the irrelevant item, but it would have some kind of response to the murder weapon. That is, if you were the actual murderer. If you were innocent, your brain's response to both those items would be pretty much the same, and it would look like this red line here. Now this response here, I'm going to put that back where it was. This response here is very similar to what the P300 looks like. P stands for positive, and in Illinois we plot positive down, which is a little confusing, so sorry about that. And then you're looking for the response, your brain's response, about 300 milliseconds into the, or I should say 300 milliseconds after whatever stimulus you presented, which in this case is the murder weapon. And then you can clearly see that there's a very big difference between how your brain responded to the murder weapon versus how your brain responded to the irrelevant item. So anyway, all I want you guys to understand about this is that when we talk about these event-related potentials or signals from the brain, we're basically just seeing how your brain responds to the pictures that we're showing you. So it's pretty basic. Okay, now I wanted to acknowledge briefly, and let me see how I'm doing on time to make sure I'm already 16 minutes in. Well, so what I want to do here is talk a little bit about neurons. I mentioned in the previous episode that neurons are kind of, I made the analogy that they're like telephone wires, that when a structure in your brain wants to talk to another structure in the brain, it sends an electrical signal through a wire, and those wires are called neurons. Now that analogy is a bit overly simplistic because neurons, I've actually drawn a neuron here for you, and you can see that it's a bit more complicated than a wire. You have a body here called a soma, and this is where it kind of manufactures some chemicals. And you have these little arms here that are called dendrites, and they reach out to and connect with other neurons. So you can see here's a tip of a neuron, and here's the dendrites reaching out, connecting to this neuron. You have the wire. This is kind of like the telephone wire part, and that's called an axon. And this is where the electrical signal is actually carried across that wire. And then you have these little suction cup looking things, which are called terminal buttons. And these terminals, you can think like an airport terminal, they house some very important chemicals called neurotransmitters, which are really important for how the brain works. These basically send messages, these chemical messages to other neurons, and that's how they communicate. So there's actually a lot of chemistry going on here. There's a lot of chemical reactions, and that's actually what's creating the electricity that is eventually, the fancy word for it is propagated or sort of channeled through the axon or the wire here. And that is how, well, yeah, I don't want to go too far into the nitty gritty here. All I want you guys to know is that neurons are, they're taking advantage of chemical reactions in the brain. And that's creating these electrical charges that are then sent through as coded information, and then they create more chemical reactions. And so that's, when we say we're measuring the electrical activity in the brain, what we're measuring is the electricity as it's being conducted across these axons. And by the way, if you didn't know, you have about 86 billion of these neurons in your brain, a ridiculous number of neurons. So that's wild. And when you get a lot of these neurons together into like a bundle, that's called a nerve. And they're basically information superhighways. So they're very cool. Now I wanted to show you guys here. So here's the brain, and this is, just pretend it's a computer monitor, and this is where we're advertising or presenting to you the stimuli, like the murder weapons. And here, let me fill this in. I'll give them a face here. So here's the head surrounding the brain. This is about where your eyeballs would be. Here's the nose, and the mouth, and chin. So there you go. There's the person. And so what we do then is that we put some electrodes on their head. And you could have literally hundreds of electrodes all over the head. In Dr. Rosenfeld's lab, we tend to use 3, something like this. And then those, of course, these electrodes have wires that feed back to an amplifier and eventually to a computer. And what you're doing is these electrodes are picking up on the electrical activity in the brain from these neurons. So hundreds, if not hundreds of thousands or millions of neurons all firing together in unison, that is creating tons and tons of electrical activity that is then picked up on the scalp, on the surface of the scalp from these electrodes. But you'll notice that these electrical signals actually have to pass through a lot of material in order to get to the electrodes. They have to pass through structures in the brain, they have to pass through the skull, the skin, the hair, all of that material just to get to the electrode, and that's actually a big problem. This is a problem that I like to think of as the cricket problem. I'm going to attempt to, I don't know if this is going to be a very good drawing, but let's say that this is a cricket. They have something like this going on, and so there's the legs. I'm sure they have other things as well, but okay, gives you the idea. That's a cricket. So the cricket problem, I don't know if you ever tried to catch a cricket. You go into nature and you'll hear the sound in the grass somewhere, and then you'll go looking for it and you won't find it. And then you hear the sound again in a bush, and then you go looking for it there and you can't find it in the bush either. And you hear it in the trees and then you can't find it there. So the cricket song, the cricket is incredibly elusive. And the cricket song is constantly bouncing off of structures in the environment, so you can never actually find the source of where the cricket is. And that's kind of the problem of what you have from the electrical signal in the brain as well, because it's passing through so many structures, it's colliding with so many structures. You have something called spatial smearing going on, where the signal gets obscured and you can't find the source, just like you'd have trouble finding the cricket. The other issue is what I call the opera issue, and I'm going to attempt to draw an opera stage. I think they look something like this, and you'd have the conductor somewhere over here, and well, I won't dare to draw wherever all the instruments are, because I just simply don't remember. But you have your percussion section somewhere, and you've got your strings and your brass and so on and so forth, and you have what could be dozens of instruments all playing together in unison, creating a beautiful song. And the brain kind of works in a similar way. You've got more than 200 structures in the brain, and what they're doing is they're all collaborating and playing in unison, if you will, and creating our conscious experience, of who we are and how we think. And the issue is that just like if you were trying to listen to an entire orchestra and you're trying to pick out one violin in the entire orchestra, that would be incredibly difficult, if not impossible. And that's also the problem here, is that you have an entire orchestra worth of activity. Your brain is always on, it never shuts off. And contrary to popular belief, or contrary to the myth, I should say, you might have heard that we don't use a majority of our brain. That's not true. You use all of it. And your brain is constantly on and constantly firing and sending electrical signals. So to pick out one structure is actually going to be very difficult, if not impossible. And because we're not even recording in the brain, we're recording on the surface of the scalp, it would be like trying to listen to a violin, one specific violin in the entire orchestra, while you're listening through a cup against the wall. It's like you're not even directly listening to the orchestra. You're listening indirectly through a cup and trying to pick out one violin, and it's just never going to happen. So those are a couple big problems of why the electroencephalograph was actually not taken seriously for a long time, because we just thought, well, what the heck? How is this possibly useful? You can't pick out a single structure, and there's so much noise going on that it's impossible to tell where the signal's coming from. So yeah, it made things really, really difficult for scientists. It took decades for scientists to be able to make any kind of sense from all this activity, all this noise going on in the brain. And their solution is actually what I already gave to you in the beginning, that what they needed to do essentially was present a bunch of pictures and measure how your brain was responding to those pictures, and average that over a whole bunch of different presentations. And eventually you would get a nice stable average at a consistent time interval. And that's how scientists eventually learned that something consistent was happening in the brain, that your brain would process this information consistently at a given time, like 300 milliseconds. And you could expect a certain type of, in this case, like a positive response. And that's, how they discovered things like P300. So anyway, I think I'm just about out of time. But I hope that that gives you guys a nice introduction to some of these concepts, the electrical activity in the brain, what's producing it, and what are some of the problems that might make it a little bit difficult to measure. And now you have a little bit of an introduction to the electroencephalograph, which is what we're going to be talking about throughout a lot of these publications. That's the technology that they use to measure the brainwaves. So I want to thank you guys so much for taking the time to listen, and I will talk to you again soon. Bye for now.